Swayam Prabha. Digital India. Educated India.
This is again a formula given by Euler. So, it is actually comes from polyhedral geometry. So, this says that suppose we have the number of vertices in a graph. So, I am going back to a planar graph, given a planar graph G. Suppose there are n vertices, m edges, and say there are some f number of faces. Okay. If you have a problem with f, say let me just use r to be the number of regions or number of faces. Sorry about that. So, then what is the relation between these three? So, n minus m plus r is equal to 2. Okay. This is the polyhedral formula, Euler's formula, and most of the time we can use this for checking also, right? The number of faces, the number of vertices, number of edges in the graph. Okay. So, the difference is the sum of all these things is going to be equal to 2. Okay. So, we will use this formula to prove most of our results in planar graphs. So, one such result where we can use this is, suppose degree of f is greater than or equal to k, say for every face f. Then what can we say about is there any relation between n and m, and of course this k. So, you know, like degree of a face is nothing but number of edges that is sitting as a boundary for it, right. And we also have, apart from this, that sum of all the degrees is equal to degree of the face is equal to 2m, right. And we also know the same with respect to vertices, right. Sum of all the degrees of the vertices is also equal to 2m, right. So, if you connect all these relations that is given, put in in front of you, what do we expect? So, I have one answer, m greater than or equal to rk by 2. Okay, that is one, you can immediately pull it out from here. Can I say something more using my Euler's formula also? Can I connect that also into it? Because I do not know how many faces are there. So, somewhere we have to kind of fit in this r, pull out the r from here. Okay, just you can rewrite it, it is going to be n minus 2 minus m is going to be negative of r. So, if you just pull it in and substitute it over here, because I know the number of vertices, I know number of edges, I know from the given graph, right, because I do not know whether the graph is planar or not till now. Okay, suppose it is planar and I know if degree of f is greater than or equal to k, then we are talking about what should be the condition, right. So, this is a lower bound, a trivial lower bound that we could get. Then I will talk about an upper bound. So, then m is going to be less than or equal to k times n minus 2 by k minus 2. Okay. So, this is an upper bound that you could get by just using these conditions. I am not going to use anything out of this, only these three formulas that we know, if you put it in right place, you will get this bound. Okay. So, if what does this say? If we have a connected planar graph, okay, here I missed one more condition. So, if we have a connected plane graph, if suppose my G is connected, because if we have disconnected, then this may not work. Okay. So, if G is connected and I also give you a plane representation, then only I can talk about the degree of f. Unless I see a plane representation, I can't tell you this, right. So, keeping this condition, we can see that this is an upper bound for your number of edges. Okay, this could be a check for you. If you are given n and m, okay, and you also know that suppose every degree of every face has to be greater than or equal to 5, then can I check whether the graph is planar or not. Okay, if it violates this condition, obviously one of the conditions above is violated. So therefore, we can immediately conclude that the graph could not be planar graph, the contrapositive of this condition. Okay. So in similar lines, we have given one condition, it is kind of necessary condition, but still not sufficient. So can we give more conditions? What should be really apt? Here we have already degree of f greater than or equal to k. Even if I don't have that information also, then how can I conclude that whether my graph is planar or not. So to see this, what we want to see is how many edges can a graph have, a plane graph can have maximum number of edges. So that is what we are trying to do here, right. We are trying to see how much maximum edges that I can have. If I add one more edge, my graph should go to a non-planar condition, right. It should jump into a non-planar status. So that will be my maximal possibility, right. So to this end, we have a maximal planar graph. A graph is said to be maximal planar if I want to add any edge out of this graph from G complement. So E belongs to G complement. If I add this, then G plus E becomes non-planar, right. So this is what is my maximal planar that I could keep. So this is the edge. After this I cannot add any more, I have reached that hectic point there, right. So now with this condition, how would a maximal planar graph look like? If I keep adding edges to a graph, right, how long can I keep on adding this edges? So where will I add edge to keep it, to maintain the planarity part, right. Say suppose I have so let me just is it maximal planar? So what else edge can I add to this? Say I have 1, 2, 3, 4, 5. 2, 4 and 2, 5, right. I can still add this 2 edges. Any more? So what have we done in this process? So if there is any cycle of length greater than or equal to 4, we could see that we can immediately add a chord to it, right. As long as we can see larger cycles, you keep adding edges to it, so that it still retains to be planar, right. So the maximal planar graph is nothing but this process is actually called as triangulation of a graph, where you kill all higher order cycles, so that it is kind of maintaining its planarity. Okay, so any maximal planar graph, okay, is going to be nothing but a triangulated graph, okay, and whichever graph we are talking about, that would be a subgraph of a maximal planar graph. So any plane, this is one point that we could think of. So any planar graph is a subgraph of some maximal planar graph, okay, of a maximal planar graph. It could be anything that, as long as you keep adding edges to it, it retains its planarity, we can have this. And what can we say about this graph? Further, anything more can we say? Yeah, that we can do, yes. So if you put it back into that formula, m is less than or equal to k times n minus 2 by k minus 2. What is my k here? If you see in my maximal planar subgraph, every face has degree 3, right. That is what we are trying to do. We are triangulating the graph so that every face will have degree 3, I mean except the outer face, right. In fact, even outer face has 3 degrees, degree 3, right. So every phase has degree 3, and so what can we say from the previous formula? My m has to be less than or equal to 3 into n minus 2 by 3 minus 2, which is 3n minus 6. So, this is a maximal planar graph. You take any other planar graph, it is going to be sitting inside some maximal planar graph, right. So, a maximal planar graph can have at most 3n minus 6 edges given any n, right. So, by using this you could also make a test for whether a graph is planar or not. If there is more number of edges than this, you can immediately conclude that the graph is non-planar. But even if after satisfying this condition, will the graph be planar? The other way around question, that is still open. I am not declaring anything on that in that direction. I am just saying, if I know m is less than or equal to this, I mean if my G is planar, then I know this is going to be true, right. That means what? If this condition is not true, obviously G is non-planar, right. The contrapositive of this, I can just relate it to this. Any other property that can we capture out of this? You all have read about connectedness, right. Number of vertices that you need to remove to make the graph disconnected. So, how many vertices you need to remove this from here to make the graph disconnected? Can I remove just one vertex and make it disconnected? If suppose I give you triangle, if I remove all the 3 vertices, then what will happen? I want to disconnect only, I do not want to empty my space, because this is also a planar graph, right. I am trying to generalize it. So, in fact, if you see, every maximal planar graph is 2 vertex connected. So, let us go into some examples. I guess you have seen a lot of theory now. Okay. So, everybody have seen this graph. Can you tell me what is the name of this? Peterson graph. So, can you tell me whether is it planar? So, what about the famous bipartite graph, complete bipartite graph on 3 vertices, non-planar, right. So, you can think about all these things. So, next is actually first I wanted to draw this, but I drew Peterson graph. So, it is also a non-planar graph. So, why is it non-planar? Can you prove this, that why it is? So, in suppose I look at K33, how many edges are there? Each vertex is of degree 3 and 9 edges, right. And we know from our previous result that my m should be less than or equal to 3n minus 6. So, what is 3n minus 6? Even the same argument you can try here also. 3n minus 6 is 12, is it? Obviously, with this, just with one condition, I am not able to use my previous theorems, right. We are still lagging in certain things. So, that is what I wanted to show. If I want to prove it mathematically, of course, I can keep on trying and I can try to draw this and try to see that there is no plane representation for these graphs, okay. But it is kind of trial and error if we want to do that. But to concretely prove it mathematically, I am trying to use the results that we have seen. Since this is not sufficient, we have got obviously 9 is less than or equal to 3n minus 6, we need something more, right. So, in this direction, I will give you another result which states that if G is a simple plane graph, with the minimum degree, right, with delta of G being less than or equal to if greater than or equal to 3, then it contains a phase of degree less than or equal to 5. Okay. So, this again you can prove using the previous results. Every vertex has minimum degree 3, right. So, use that and into your Euler's formula you can conclude that there is at least one phase which will have degree at most 5. And similarly, we can also say that, So, if we have a simple graph, again if G is simple plane graph, here I am just giving you, throwing you the results because I am leaving it to you to explore these parts. Then my minimum degree itself has a bound. Okay, I cannot have more, I mean my minimum degree has to be only this much. I cannot have a minimum degree graph say having some 10, that is every vertex has 10 as a degree, right, at least 10 degree, right. So, this restriction is again you can prove it. So, the condition is that if your graph is plane, simple plane graph, then minimum degree for the graph should be not more than 5. Okay. So, now if we use these conditions into our previous K33 or K5, you can prove that these one of these conditions would be violated. Okay. Okay. So, now let us go into the thing that we are waiting for to prove Kartowski's theorem. Of course, I am not going to prove it, okay. So, do not worry. Again I am going to throw in a concept which you have already seen, which sir has been using it when he was proving a lot of theorems, okay. The concept of subdivision. These things come in handy for you when you try to prove something else also. So, you can just learn these techniques or ways to use them, then you can just use it anywhere else also. It is not restricted only to this part. Okay. So, what is a subdivision? A subdivision of an edge is nothing but if you have an edge uv, when I say I subdivide this edge, I mean that I will add a vertex between these two edges. Okay. Either 1 or 2 or 3, I can add as many as I want, I do not have any restriction on that. But a subdivision is nothing but for a graph G, S of G is going to be a subdivision graph where some of the edges I just divide them and I introduce a new vertex in between, that is I replace the edge uv by two edges uw and wv in my edge, in the edge set, corresponding edge set. Right. So, like this I could keep on subdividing, I can also introduce one more, right. So, in this case what I am doing, I am replacing uv by 3 edges uw, ww1, w1v, right. So, this is a the idea of subdivision. So, what does this subdivision do to the graph? Can it disturb my hereditary property? Obviously, I am not going to subdivide if two edges are going to cross, I do not subdivide it and I add an edge over here, vertex over there, okay. That I am not doing, I am only doing where I can just subdivide an edge, okay. That is I am dividing, changing my edge into a path, I am converting an edge to a path of certain length, right. So, if you see the properties of these planar graphs and subdivision, so we have certain interesting properties that come from. Suppose I have a subgraph of G, right. We have seen already that if G is planar, then H is also planar, that is the hereditary property we have been talking about. So, what can I say about the other way round, about non-planarity? In similar lines, can I write something? If H is non-planar, then I can immediately say G is also non-planar, right. One way for when G is planar, I know subgraphs are all planar, but if I know if it has one non-planar subgraph, then I can immediately conclude that my graph is also non-planar, right. So, in this line, I can immediately see that S of K5, the subdivision of K5, right. So, I can also say one more result. If G is non-planar, implies S of G is also non-planar. I am not disturbing the planar property here, right. So, if G is non-planar, then S of G is also non-planar. So, from here we can conclude that if, so since we know that K5 and K33 are non-planar, the subdivision of K5 and K33 are also non-planar, right. So, now can can you all visualize where I am heading to? So, I have given you a list of items, bullet points that I am trying to target, right. S is subdivision of K5, subdivision of K33 are all non-planar. I know because K5 and K33 are non-planar. So, can I now say that by using this second point, can I combine second and this fourth one to say something? So, can I say that if G contains S of K5 or S of K33, then G is non-planar, right. So, if I want to write the contrapositive of this, I can write if G is planar, then G does not contain a subdivision of K5, it implies, it is an implication, right. G planar implies G does not contain a subdivision of K5 and K33. So, can we talk about the reverse implication? This is what Kartowski proved. Okay. He proved that G is planar if and only if. So, one way it is immediate, we can see, right. So, the converse, that if G does not contain a subdivision of K5 or K33, then G is planar. Okay. So, this is what Kartowski's theorem states, the converse, both, it is if and only if, right. If G is planar, if and only if G does not contain a subdivision of K5 or K33. So, obviously do not worry, I am not going to prove it. So, before I close, I will just give you one example, and let us go back to this Peterson graph. We have not talked about it much. So, can you show that we know this is a non-planar graph, right. So, we know it, at least by practice we have been seeing it is not possible. So, can you give me a subdivision of K33 which is going to sit inside my Peterson graph? That is, I need to introduce vertices to K33 here, right, such that that would be a subgraph, that becomes a subgraph of this Peterson graph. Say, let me just give you, even let us be specific, say 1, 2, 3, 4, 5. So, now can you give me a subdivision for this, so that, or give me labelings and a subdivision, so that I can simply say that okay, this is a subdivision. So, Peterson graph is not a subgraph of this. Give it a try. So, there are 6 vertices here. So, that means what, you need to introduce 4 vertices, right, or can you introduce, like you can try introducing one at a time and see whether that subdivision is going to be a subgraph of Peterson graph. Okay. So, if you can do it, then we can immediately say that the graph is non-planar, right.